So now we are going to explore an interesting concept in algorithm analysis called the master method. So imagine you are trying to solve a problem using a divide and conquer approach. This means you break down the problem into smaller subproblems, solve those subproblems, and then combine their solutions to get the final answer. Now, the master method is like a handy tool that helps us figure out the time complexity of such algorithms. So, the function we use for this is the function t of n equals a times t of n over b plus f of n. So, let's break down what these variables mean. N stands for the size of the input we are working with. A represents the number of subproblems that the recursion gets divided into. And n over b tells us the size of each of these subproblems, and we assume they are all the same size. F of n is the work done outside the recursive call, like the cost of dividing the problem into subproblems and then merging their solutions. So it's important to note that the a has to be greater than or equal to 1 and b must be greater than 1. Also, function f of n should be a function that becomes positive as n gets larger. So, how does this help us? Well, the master method offers us a simple and quick way to calculate the time complexity of our divide and conquer algorithms. It's like a shortcut that saves us from doing complex math every time we encounter a recursion. This method makes analyzing algorithms much more manageable. In summary, the master method is like a magical formula that lets us peek into the future and see how our divide and conquer algorithms will behave as the input size grows. It's a powerful tool that simplifies our work and helps us understand the efficiency of our algorithms much better. Imagine you are faced with a tricky problem that keeps breaking down into smaller versions of itself. So you want to know how much time it will take to solve the big problem based on how long it takes to solve the smaller ones. And that's where the master theorem comes into the picture. Here's the formula we use. The function t of n equals a times t of n over b plus f of n. In this formula, a represents how many smaller subproblems you divide the main problem into, and b is how much you shrink the problem size of each subproblem. Function f of n stands for the extra work we do outside of solving the subproblems. Now, let's look at the results. If the extra work f of n is not too big compared to the reduction in problem size and it's still much smaller than n times logarithm base b of a, then our final time complexity will be dominated by the work in the last level of recursion. If the extra work f of n is about the same as the reduction in problem size, then our final time complexity will be n times log base b of a times log n. If the extra work f of n starts to become more significant than the reduction in problem size and it's bigger than n times log b base of a, then our time complexity will be influenced mainly by the extra work. So these rules help us quickly figure out how long our algorithm will take to solve a problem. The master theorem is like a guide that helps us avoiding get lost in complex calculations and focus on what really matters for understanding the time complexity of our algorithms. Let's dive into a solved example of the master theorem to see how it actually works. So imagine you have an algorithm that breaks a big problem into 3 smaller subproblems, and each of those subproblems is half of the size of the original problem. Also, the extra work you do outside of solving those subproblems is proportional to n squared. Here's the formula we are working with. The time function t of n equals 3 times t of n over 2 plus n squared. Now, we are going to use the master theorem to understand how long this algorithm will take. First, let's plug in the values we have. A is equals to 3 because we are dividing the problem into 3 subproblems. N over B is equals to N over 2 since each subproblem is half the size of the main problem. F of n is equals to n squared because that's the extra work we are doing. Now, we calculate log base b of a. Log base 2 of 3 is about 1.58. Since 1.58 is less than 2, we move on to the case where f of n is less than n to the power of log base b of a raised to a constant. In this case, n log base b of a plus epsilon would mean n to the power of 1.58 plus some constant. But because f of n is just n squared, which is smaller than that, we are in case 3. So according to the case 3, our time complexity is same as the extra work we are doing outside the subproblems, which is theta of n squared. So that's the deal. The master theorem helps us quickly figure out that for this algorithm, the time it takes is proportional to n squared. So it's like a shortcut for understanding time complexity in certain cases. Alright, let's talk about some situations where the master theorem might not be your go-to tool. You see, the master theorem is pretty nifty, but it has its limitations also. It's not a one-size-fits-all solution. Here are some cases where it won't come to your rescue. If the function describing the time complexity, so let's say it's a t of n, isn't always increasing or always decreasing as n grows. For instance, if you have something like t of n equals sine of n, where the function is waving up and down, the master theorem might throw its hands up and say, I'm out. Also, if the extra work you are doing outside the subproblem f of n isn't something simple like a polynomial. Imagine if f of n equals to 2 raised to the power of n. The master theorem might not be able to give you a clear answer in this case. Another thing, if the number a, which tells you how many subproblems you are dividing the main problem into, isn't a constant, then the master theorem might not be your best buddy. Imagine if a equals 2 times n. That's not a straightforward constant, right? And here's one more. If a is actually less than 1, well, the master theorem isn't designed to handle the situations either. It meant for cases where a is greater than or equal to 1. So, while the master theorem is pretty cool for many situations, remember that it's not a superhero that can handle every problem out there. It has its limitations, and in those cases you might need to roll up your sleeves and use other methods to figure out your algorithm's time complexity.